So can you guys hear me?
Yes.
Yep.
Thanks. So sorry, hello, can you still hear me?
Yeah.
Yep.
So are there any questions about the material? Okay, so I don't think you have homework. I don't put up the learning curve and the homework assignments. I just put up the due dates. So they didn't put up homework for you. So I guess you don't have homework. You just don't have the learning curve stuff this week. And then next week I'm gonna try to post a quiz, which will be due by Friday. It will be about the dot product and the cross product. So yeah, that's how basically the next week will look. So let's do a brief summary of the dot product, and then we can continue with the cross product. So second. Okay. Fine. So again, the dot product, you just take each component and you multiply them. We know that it's commutative. You can move around the scalar, and v dot v is equal to v squared. And then the most important equation is this equation over here, which is that v dot w is equal to the magnitude of v times the magnitude of w times cosine of the angle between your vectors. And then we said that a good test to see if v and w are orthogonal is if their dot product is equal to 0. And every u can be decomposed into its projection onto v. So here's my u. I can decompose it into the projection onto v, and then into the orthogonal component. And then u is equal to u projected onto v plus u orthogonal to v. Okay, and then the projection is just the component of the vector, which is u dotted with v over the magnitude of v, multiplied by the unit vector. And the orthogonal component is just u minus the projection. Okay, so let's continue with cross product. Okay, so one of the biggest uses of the cross product is if you have, let's say, a wrench and you apply force to it at some point. So different vectors of forces can be applied to this wrench at different places. And if you want to know the torque, it's going to be equal to R. So the distance from the point where the force is being applied cross F. That's going to be your torque. So that's in physics a fairly important use of the cross product. But the intuition behind it, let's first talk about why the cross product is useful. So you have two vectors. This is your vector v, this is your vector u. Then, actually, let me call this w. Then the cross product between them, v cross w, is going to give you another vector, and it's going to be the vector orthogonal or perpendicular. So there's a 90-degree angle between this vector, this is the vector over here, v cross w, and the vector v and the vector w. So, yeah. Again, here's your v, here's your w. Your cross product is going to be another vector. Orthogonal to it, it can either be going in that direction or it can be going in the other direction. And we'll see a way of figuring out which way it's going. But it is going to be orthogonal to V and to W. And yeah, so that's the geometric interpretation of the cross product. You can also imagine a plane over here. So imagine that V and W are sitting in a plane. There's always a plane that you can find that V and W will be sitting in. Then your cross product will be the vector orthogonal to the entire plane, or it's called the normal vector. So we're going to talk more about that when we get to planes. But yeah, for now, sorry. So yeah, so the cross product, like I mentioned, it takes two vectors. So you're going to take a vector and put it in here. You're going to put a vector in here, and it's going to output a vector. So the output is also going to be a vector. So in order to be able to compute cross products, we first need to know how to find determinants. So let's talk a little bit about determinants. So for a matrix, let's first talk about 2 by 2 matrices. And it's going to be a matrix, let's say A, B, C, D. And the determinant of this matrix is going to be A times D minus B times C. And another way of writing the determinant of a matrix is just instead of doing the determinant of this matrix, if you have if you have flat lines A, B, C, D like this, then this means the determinant of this matrix. So if you have like lines that are curved, this is your matrix, and this would be the determinant of the matrix. Or you can just write the determinant of your matrix, and that's what it is. Any questions about this? Is it clear?
Yes.
Yeah. Okay. So now let's try to look at the determinant of a 3 by 3 matrix. So if I have a 3 by 3 matrix, let's call this A1. A1, A2, A3, B1, B2, B3, C1, C2, and C3, and I take its determinant, then this is going to be, well, you first go to A1 over here, so we're going to write A1, and then we imagine that this line and this line get canceled out from A1, so we're left with this matrix over here. So we multiply by the matrix B2, B3, C2, and C3. Okay, and then let's rewrite this. So this is A1, A2, A3, and this over here is B1 and C1. So then we're going to subtract, so they alternate. We're going to do plus A1 times this matrix minus, and then we go to A2 over here, A2, and we can again cross out these lines. So we're going to be left with the matrix B1, B3, C1, and C3. And so we're going to take A2 times the determinant of that matrix. Okay, and then then we're going to go on to A3. We're going to cross out these lines. So this is going to be plus A3 times the determinant of the matrix B1, C2, C1, and C. Okay, one second, B2. Okay. Okay, B1, B2, C1, and C2. Okay. So now this is going to be equal to A1 from here times the determinant of this matrix is going to be B2C3 minus C2B3 minus C2B3. Okay, minus, and then we go to A2 over here, times the determinant of this matrix, which is B1 C3 minus C1 B3. Okay, plus A3 times B1 C2, so B1 times C2 minus C1 times B2. And that's going to be the determinant of this matrix. Any questions about this?
I have one question. Why is A2 being subtracted and then the A3 is addition?
Yeah, so they alternate. So you just have to remember this is plus, minus, plus.
Okay, thank you.
All right. So now, so let's look at this. So for this 2 by 2 matrix, for example, so we want to find the determinant of 3, 2, 1/2, and 4. Well, that's going to be 3 times 4 minus 2 times 1/2, which is going to give us 12 minus 1, which is going to be 11. And then for the determinant of a 3 by 3 matrix, like we talked about, you do A1 times the determinant of the matrix that it leaves over minus B1, determinant of that matrix, plus C1, determinant of the matrix that it leaves over. And yeah, when you're up to, let's say, B1, first, again, you're a minus over here, and you cancel out these rows, this row, this column, and you're left with A2, C2, A3, and C3. And yeah, so let's try to calculate the determinant of the following matrix. 1 second. Yeah, okay, so let's try to calculate the determinant of the matrix 2, 4, 3, 0, 1, -7, -1, 5, 3. So the determinant of this matrix is going to be 2. Okay, let me actually do it on the other page. Sorry. Okay, so it's going to be 2, 4, 3. Zero, 1, -7. -1, 5, 3. -1, 5, and 3. Okay, so the determinant of this matrix is going to be this 2 times the determinant of the matrix 1, -7, 5, and 3, minus 4 times the determinant of 0, -7, -1, and 3, right? For the 4, we go there, 0, -7, -1, 3, plus 3, that 3 times the determinant of 0, 1, -1, and 5. So this is going to be equal to 2 times 1 times 3 minus, but then there's a minus here, so that becomes a plus, 7 times 5. Yeah. Okay. Minus 4. That's that 4. Okay. And then we have a minus, but they cancel. But we have a minus from the whole thing. So this will become plus. And this is going to be 7. And then from the last one, we're going to have plus 3 times. And then this is 0. And then we have a minus over here, but it cancels with this minus. So it's this just 3. Okay, so this should be our determinant. Yeah. 4 minus 7. 1 second. Oh yeah, perfect. Yeah, so that's our determinant. Any questions about that?
Is the notation for a matrix the same as the notation for a determinant, or is that first part with like the 3x3 part just telling you what the operation is? So it's telling you take the determinant of that matrix.
Right, so the matrix would be using curly bracket, not curly, but kind of brackets like this. So that would be 2, 4, 3, 0, 1, -7, -1, 5, 3. This would be the matrix, but then if the lines are flat, then this is the determinant.
Okay, thank you.
So now let's continue with the cross product. So if you have two vectors, v, which is going to be equal to v1, v2, and v3, and w, which is equal to w1, w2, and w3, then the cross product between them, which we'll call v cross w, is going to be, and you're going to take the determinant of the matrix with an I here. So in the first row, you put an I, a J, and a K. And in the second row, you put the V because it's first. So you put V1, V2, and V3, and W1, W2, and W3. And now you take this determinant. So that's going to be equal to your I times V2, V2 times W3, V2 times W3, minus V3 times W2, minus V3 times W2, minus J times, so here's your J, V1 times W2, V1 times W2, minus, the W1 times V3, W1 times V3, plus now you go to your K, and now we have V1, W2, V1, W2, minus V2, W1, V2, W1. And in vector, well, in the other vector notation, we are going to have that the first component is going to be V2, W3, minus V3, W2. The second component, I'm just going to put the negative in, so it's going to be W1, V3, W1, V3, minus V1, W3. And the third component is going to be V1, W2, minus V2, W1. And that's going to be your cross product. So this is your cross product, this vector. Right there, cross product. Okay. Any questions about this?
Yeah, so why is the second part of that new notation, you have W1 V3 as the positive one minus V1 W3, but in the part above there, you have minus J times V1. Oh, never mind, it switches with the sign, yeah.
Yeah. Okay, so now there are a couple of important questions to think about. And the first one is, why is it that this gives us the orthogonal vector to both v and w? Because like I said, the important part about the cross product, actually the most important part about the cross product, is that if you have v and w, the cross product gives you the vector orthogonal to them. So the question is why is this? And the answer is that's fairly complicated, but let's first try to understand what a determinant even is, and then later we might actually come to this over here. So actually, let's first start with trying to prove that this is true. Not trying to understand that it's true, but let's at least just try to prove that it is true. So we know that if a vector is orthogonal to another vector, then then their dot product is 0. So if I take the dot product of v dotted with v cross w, the question is this thing equal to 0? So let's do it. So v dotted with v cross w, that's going to be equal. So let me just rewrite this so we can see. v1, v2, v3 dotted with v cross w. So that's just going to be equal to v1 times this component down here. So that's v2, w3, v2, w3 minus v1 times v3, w2. Okay, and now plus, and now we're going to have the v2 times this component. So it's going to be plus v2 times the component w1, v3 minus v2 times v1, w3. Now plus, and then we're going to have v3 times this component. So that's going to be v3 times v1 times w2 minus v3 times v2 times w1. Okay, so now this over here, v1, w2, w3 cancels with this, v1. No, it does not. Sorry. Okay, let's try that again. It will cancel with v1, w2, but not that one. Okay, no. Sorry, v1, w2, but then this is v3.
Should be v2 for w2.
This should be v2. This is.
Oh no, it's the first one.
This should be. Oh, this should. Sorry, 1 second. v1. V2. Thank you. Okay, so let's try it now. Okay, so yeah, v1, v2. Okay, perfect. So these do cancel. Then v1, v3, w2, v1, v3, w2. These cancel. And then v2, w1, v2, w1, and v3. So these cancel. So this is equal to 0. So check. So they are orthogonal. You can do the same thing with w. So w dotted with v cross w should also equal to 0. And even though, so 1 second. Okay. And the same thing will be true for w cross v. W cross v does not equal v cross w. We'll see what it does equal later. But v dotted with w cross v should be equal to 0. And again, so let's talk about what this is. So here's my v, and here's my w. So one of them, I'm not saying which one, we'll see later, will be this vector. Maybe it's this one. And the other one will be this vector. So you just flipped it. So So because they're both orthogonal to V and W, both of them are, so this is also going to be equal to 0, and this W cross V will also be equal to 0. Okay. Now, I do want to explain briefly what determinants are, just so that you know, even though it's not completely relevant to multivariable and it's more relevant in linear algebra, but it is important to know the geometric interpretation of a determinant. So I'm going to explain that briefly. If you have a linear map, let's say from R2 to R2. So this is a linear map, T from R2 to R2. Second. All right. So what is this? Here's my R2. And I can take vectors here. Let's say that's a vector. And then I can look at their transformation under T. So I can see where this T is going to take vectors to vectors, but linearly. So we'll see what that means in a second. But it's going to take this vector, let's call it V, to, let's say, this vector, which is going to be the vector TV. So after the transformation. And it does that to every vector actually in R2. So here's another vector, and maybe it's transformed to here. So here's going to be W, this is going to be TW. What does it mean for this to be a linear transformation? Well, it would mean that T of two vectors, V plus W, is equal to T of V plus TW, and that T of some constant, lambda times V, is equal to that constant times T of V. Okay. Now, there's a theorem that says that any linear transformation, so if it's from R2 to R2, then the theorem says that any linear transformation T can actually be written by a matrix A, B, C, D, with some numbers A, B, C, and D. And the way it transforms a vector, so let's say it transforms the vector V, which is going to be V1, V2. Well, the transformation is just going to be V1 times AC plus V2 times BD. And this is going to be, so if we write this in vector notation, well, in our vector notation at least, so it's going to be V1, this is a number, so it's going to be V1 times A, so sorry, let me do it the other way. It's going to be AV1 plus B V2. That's going to be my first component. And then the second component is going to be CV1 plus a D V2. And this is going to be my vector TV. So this is the transformation. Okay, so now so every linear transformation can be written as a determinant, and every determinant can be written as a determinant where you do the following operation in order to get that linear transformation. And now that we have this matrix, we can, I'm sorry, I think I said determinant, I meant matrix. But now that we have this matrix, we can look at its determinant. So let me erase, okay, let me just do it up here. We can look at the determinant of this matrix, right? Of A, B, C, D. Like I said, this is A, D minus BC. So what is this? Well, let's go to the transformation here, and we can imagine that we're looking at a box with area 1. So this is a box with area 1, and we watch it, we look at where it goes after the transformation. It can turn, let's say, into a diamond, that's a possibility. And let's say that the area of this diamond is 3. So this box with area 1 turned into a diamond with area 3, then the determinant will be equal to 3. And it won't only be true for this box. If the determinant is 3, it's 3 for everything. So that means that a box here with length 1, wherever it goes under the transformation, maybe it turns into something that looks like that. I don't know. this will also have area 3. Or this box, wherever it goes, this area will be 3. And that's what the determinant symbolizes. Any question about this or represents or helps you find? Any questions?
No question.
Okay. So the same thing is true for a 3x3 matrix. It represents a map from R3 to R3. And the determinant is, it shows you how a box with area 1, it will tell you its area under the transformation. Okay, so now going back to here. So here's our cross product. Yeah, V cross W, it's going to be I times this matrix minus J times this matrix, and so on. Okay, so let's do the following problem. So they ask us to find V cross W for V equals this and W equals that. So V cross W is going to be equal to the determinant of the matrix I, J, K, and then negative 2, 1, 4, 3, 2, 5. And then this is going to be I times 1 times 5 minus 2 times 4. So that's 8. Minus J times negative 10, right? Negative 10 minus, sorry, 1 second, 12. Plus K, so that's K, times negative 4 minus 3. Okay, and this is the vector. So this is 5 minus 8, so it's negative 3. And this over here is negative 10 minus 12, so it's negative 22. And this over here is negative 4 minus 3, so it's negative 7. So that's going to be my vector V cross W. And if we were to change this, so if let's say we wanted to look for W cross V, so now the W is first, so you would put I, J, K, and then you would go for W first, so W1, W2, W3, and then V1, V2, V3. Okay. So, any questions about this? Okay. So let's now look at the following figure. This figure will help you know if your vector, again, if you have a vector V and W, we can think about the plane that that V and W lie in. And we want to know, so now here's the vector U, but this is vector U is equal to V cross W. And we want to know if U is going in the upwards direction or the downwards direction. So what you should end up doing is you should put your fingers in the direction of V and the palm of your hand in the direction of W. And V and W are going in some, so if this is V and this is W, then your fingers go here. The palm of your hand goes here, so your hand looks something like this, with here are your fingers. And then you look at your thumb, and if your thumb is pointing upwards, then V cross W is pointing upwards. So, and this is where your fingers go in the first one. So if you're looking, let's say, at W cross V, then your fingers are going to go here at W. So sorry. So let's just draw it. Here's W, and here's V. then your fingers go in the W direction. So here are your fingers. And then the palm of your hand is here. So your hand has to be upside down. So your thumb is pointing in the downwards direction. And so we know that W cross V is pointing in the downwards direction. Any questions about this? Okay. So yeah, the fingers of your hand should be curled from V to W, and then you look at your thumb to see what direction you're in. Okay, so here are some very important properties of the cross product. So the first one is that V cross W is orthogonal to both V and to W. Give me 1 second. So that's the first property. The second property is very important. Geometrically, it comes up a lot in proofs. So the magnitude of, the magnitude of V cross W is equal to the magnitude of V times the magnitude of W times sine of theta. So let's look at a couple of interesting things about it. First, it's fairly similar to the equation that we had for the dot product. That was V dot with W is equal to the magnitude of V times the magnitude of W times cosine theta. Again, this theta is the angle between V and W. Now, a couple of differences are we don't look at the magnitude for this one because it's already a constant. And of course, this is a constant. But in this case, this is a vector. So we have to take its magnitude, and that's going to be equal to that. So the cross product resembles sine. It kind of behaves the way sine is. And what do we mean by it behaves the way sine does? Well, sine is a projection onto the y-axis, right? Generally, in Cartesian coordinates, or at least the transformation from Cartesian coordinates to polar coordinates is that y is equal to r sine of theta, and x is equal to r cosine of theta. So the cross product will help us find y, the y component of vectors if we need to. So here's my vector. So the cross product, or at least if I have two vectors, especially, but okay, we're going to see more about this in a second. But the cross product kind of does what sine is supposed to do. It projects things onto the y coordinate. And the dot product, as we've seen, does what cosine is supposed to do, and it projects things onto the x-axis, which is why the projection of V onto the component of the projection of, let's say, V onto W is equal to V dotted with W divided by the magnitude of W. So this over here is because of this cosine. So in a similar way, we're going to use sine to try to find y. But yeah, so the length of V cross W is the magnitude of V times the magnitude of W times sine theta. Okay, and this is actually not that interesting, except for, yeah, we need to know the right-hand rule to be able to figure it out. So that actually is important, but whatever. So should not cross it out, whatever. Anyway, now let's look at the following example. So let V equal to this, W equal to this. They want us to find V cross W using geometric properties of the cross product rather than the equation. So they want us to find this using this fact that the magnitude of V times the magnitude of W times sine of theta is equal to the magnitude of V cross W. So this is not very relevant to, you know, multivariable, just because generally we will be able to look at this equation and you don't necessarily want to figure out what V cross W is from the geometric properties. So I'm actually not going to go through this. But if you want to go through it with me at some point by yourself, yeah, let me know. Okay, so now very interesting. It's something that makes sense. V cross W is equal to negative V cross W. And that's because that, well, simple geometric interpretation is that you know either way that the vectors are orthogonal. So if here's my V and here's my W, then we know that V cross W is orthogonal to both of them, which means the W cross V must also be orthogonal to both of them. Sorry. But this is just the opposite vector of this, and this tells us that V cross W is equal to negative W cross V. Okay. So here are some, oh, and here's a nice picture that represents what I just drew. So here are some properties of the cross product. Like we said, W cross V is equal to V cross W. V cross V is equal to 0, which makes sense if so now if you're looking at V cross V, well, the magnitude of this, so the magnitude of V cross V, that's equal to the magnitude of V times the magnitude of V times sine of the angle between V and V, which is sine of 0. So this thing is 0. But if the magnitude of your vector is 0, then your vector is 0. So that means that V, oh, sorry. That means, sorry, this is 0, but that means that V cross V is equal to 0. If the magnitude of your vector is 0, then your vector itself is also the 0 vector. So that's why V cross V is 0. Okay. So now V cross W is equal to 0 if and only if either W is equal to lambda V or V is equal to 0. So let's try to think about what happens first if W is equal to lambda V. So if W is equal to lambda V, we go back here, we do the exact same thing, but this time we're looking at the magnitude of, so we're looking at the magnitude of V cross W, which is equal to the magnitude of V cross some scalar times V, because that's what W is. And this over here is going to be equal to the magnitude of V times the magnitude of lambda V times sine of 0. Sorry, sine of 0, which is also equal to 0. So that means that the magnitude of V cross W is equal to 0. So that means that V cross W is equal to 0. So if you have two vectors which are parallel to each other, so here's my vector V and my vector W, then V cross W is going to be 0. And obviously the other direction, well, if V is 0, then this will be 0. That's pretty easy to see. Okay, and then these properties are also, constants can move around and you can distribute the cross product from both directions. So fairly important. And okay, another thing about the cross product is what it does. It's interesting to look at what it does to the I, J's, and K's. So the I, J's, and K's are all orthogonal. So if you look at I cross J, you need to find the orthogonal component of I cross J. And well, it's going to either be K or negative K. You can try to look at the right-hand rule, and you'll see that it's K. J cross K is going to be I, and so on. So we have these relationships that just come out of the fact that each one of these vectors, we need to find, for the cross product, we need to find a vector orthogonal to them. So the vector orthogonal to I and J is K, and so on. And obviously, I cross I, J cross J, and K cross K are 0. So you can use these relationships to find what this is. You distribute it, and then you just look what I cross J is. I cross J is K, so that will be K. I cross K, so I cross K is negative J, so that's going to be negative 10J, and so on. Okay, I think for today, we're going to stop here. Are there any questions about what we did today?
No, I'm good.
Okay, so yeah, let's stop here, and I'll see you next week. Okay, thank you.